Good morning, welcome to new lecture. Today I will talk about moment of inertia. In static we call it area moment of inertia or second moment of area. First I will define the term, then I will explain the concept, then I will compare with another moment of inertia we have in dynamic course or physics course, and maybe you heard about that. What is the second moment of area or area moment of inertia? The second moment of area or area moment of inertia, or most of the time you will hear moment of inertia. Moment of inertia is a geometrical property of an area or cross section which reflects how its points are distributed with regard to an arbitrary axis. The second moment of area or area moment of inertia or moment of inertia is denoted with an I for an axis that lies in the plane, or a J for an axis perpendicular to the plane. So, I will read this definition. The second moment of area or area moment of inertia or moment of inertia is a geometrical property of an area or cross section which reflects how its points are distributed with regard to an arbitrary axis. The second moment of area is denoted with an I for an axis that lies in the plane, or a J for an axis perpendicular to the plane. This is the definition, but when we will use it and why we need it. area moment of inertia is a measure of how much resistance that cross section has to bending. What does that mean? Assume we have one lumber or beam from wood and the cross section is rectangular. For example, the cross section it is 1 inch by 4 inch. This is the cross section. And you use this lumber in order to cover one span, simply supported beam. And you will put one weight here, for example, 200 pounds, anything. You can place this lumber in this direction or the same lumber cross section 1 inch by 4 inch but in this direction. So now if we put in this direction, the bending axis will pass from centroid, it will bend respect to this axis. If we put in this direction, if we rotate and put in this direction, this is 1 inch, now this is 4 inch. We can put in this direction. Both of them it is possible. Which direction is good? In which direction it will resist against bending moment more? Here we have one concentrated load or weight at midspan, and we know the maximum bending moment it will be at midspan. So if we put 1 inch by 4 inch, we will have a little bit deflection or sagging, and the maximum deflection will take place at midspan. For example, deflection it is quarter inch, 0.25 inch. If I rotate and put in this direction, the sagging or deflection will increase. The sagging or deflection will increase. The reason, the resistance against bending moment will decrease. For example, look at this wood trim. Assume this is a beam. Now if I put this wood trim or beam in this direction, I can bend it. I should apply force, bending moment, but I can bend it. But if I rotate in this direction, I cannot bend it because it is very strong. The cross section is the same. Both of them, for example, in this example, cross section 4 times 1, so 4 inches square. Again 4 times 1, 4 inches square. The cross sectional area is the same, but the resistance against the bending moment will change. And you see in this direction is much stronger than this direction. This is we will measure using second moment of area or area moment of inertia. In most cases you will hear moment of inertia. In static and strength of material and structural analysis courses, whenever we are talking about moment of inertia, it means area moment of inertia or second moment of area. It means this definition, area moment of inertia is a measure of how much resistance that cross section has to bending. We have another moment of inertia we will use in dynamic course, that is mass moment of inertia. That is mass moment of inertia. Mass moment of inertia definition is different. if I want to define mass moment of inertia, I can say mass moment of inertia of a solid measures the solid's resistance or solid's ability to resist changes in rotational speed about a specific axis. So this is mass moment of inertia. In dynamic course we will use, in physics course we will use the mass moment of inertia. You see, mass moment of inertia measures the solid's ability to resist changes in rotational speed about a specific axis. The larger mass moment of inertia the smaller the angular acceleration for a given torque. So, the larger mass moment of inertia will cause the smaller angular acceleration for a given torque. This is difference. So, in static course, strength of material or mechanics of material, structural analysis, moment of inertia means area moment of inertia or second moment of area. And we will show usually with I. And polar moment of inertia we will show with J. Later on I will explain. But mass moment of inertia we will use in dynamic course, in physics. Mass moment of inertia measures the solid's ability to resist changes in rotational speed against a specific axis. Again, mass moment of inertia is shown using I. We will show with I. So let's see how we can calculate moment of inertia or area moment of inertia. Area moment of inertia, for example, for one shape like this, respect to a given axis. For example, this axis passes through the centroid. So x, c, y. C, I want to calculate area moment of inertia. In order to calculate that, if I assume one small element, dA, Ix will be equal to dA, area for this differential element, times the distance up to x-axis is square. So it will be y squared times dA. Because this is moment of inertia for one small element, this is dIx is equal to y squared dA. If I want to calculate for entire cross section, I can write Ix is equal to summation of y squared di. So I will divide this cross section to different segments. and each one distance up to x-axis, and I varies from equal to 1 to n. So this means if I want to define precisely Ix is equal to integration y squared dA. In a similar way, Iy, area moment of inertia respect to y-axis, it will be equal to integration x squared dA, dA the area for this element, and x squared the distance of this element up to y-axis. So, we will use this formula in order to calculate moment of inertia. Let's calculate moment of inertia for very simple shape, for rectangular shape. For rectangular shape, for example, I have one rectangular and axis passes through centroid. If I assume one strip element like this, the thickness for this element is dy, the distance up to x-axis it is y, and the width for this rectangular it is b, the height is h. In that case, Ix is equal to integration y squared dA. Here it will be integration dA. The area for this strip will be b times dy, and y varies from negative h over 2 to positive h over 2. So this will be b y cube over 3 from negative h over 2 to positive h over 2. If we plug these, I will end up with b h cube over 12. By switching width and height, I can define moment of inertia Iy respect to y-axis. It will be hb cube over 12. So, for rectangular shape, I found the moment of inertia respect to x-axis. If x passes through the centroid, it will be bh cube over 12. Respect to y, if y passes through centroid, it will be hb cube over 12. For different shape like round shape or triangle shape or trapezoid shape, again, you can integrate and find it. But in order to make calculation much simpler, in all static books or strength of material books, there are appendix, there are table. For different shape, you can find the moment of inertia. It means they integrated and they came up with formula. But those table most of the time gives moment of inertia respect to the axis passes through the centroid. If this beam or this cross section bends respect to axis passes through the centroid, that is right moment of inertia. But if we want to calculate respect to another axis, we should modify that. We should transform that. How we will modify it? In order to modify that, we should integrate like this, or we can use another formula. For example, here you have this shape, you find the moment of inertia respect to those axes passes the centroid. So the centroidal axis moment of inertia is given, you know that. Now you want to find respect to another x-axis which is parallel to these axes. And the distance between these, it is d. So this is x and this c, this is x. Ix, the moment of inertia respect to this new axis is equal to IXC, moment of inertia respect to centroidal axis, plus the area for this cross section A times d squared. Pay attention, these two axes, they should be parallel, and d is the distance between two axes. So if we have now moment of inertia respect to those axes passes through the centroid, we can transform, we can modify to any axis parallel to those with this formula. Ix is equal to Ixc plus area, cross-sectional area, times d squared. D is the distance between two axes. This formula, they call it the parallel, let's say right here, the parallel axis theorem. So the parallel axis theorem means if we have moment of inertia respect to those axes passes through the centroid, we can transform those moment of inertia to any other axis parallel with those using this formula. Ix is equal Ixc plus area times d squared. D is the distance between two axes. Now let's, for this rectangular, I integrated and I found respect to axis passes through centroid. Ixc, answer was b, h cubed over 12. How about this axis? If I call this x, Ix is equal to Ixc plus a d squared, the parallel axis theorem. So I can plug b h cubed over 12 plus area for this cross section. It means b times h times the distance between two axes. This distance is h over 2 times h over 2 is squared. D squared, h over 2 is squared. So this will be b h cubed over 12 plus b h cubed over 4. The answer will be equal to b h cubed over 3. The reason we needed something, sometimes bending take place respect to axis is not passes through the centroid, or for example, if we have T section, I section or something like that, we should able to transfer from one axis to another axis. I will do that, you will see. For example, I have section like this, T section, 1 inch, 4 inch, 2 inch, 6 inch. I want to find moment of inertia respect to x. First step, I will divide this shape to two rectangular number 1, for example, rectangular number 2. Now, for rectangular number 1, Ix, for rectangular number 1, respect to that axis passes the centroid, it will be 1 times 4 cube over 12. But pay attention. It is 1 times 4 cube over 12 respect to the axis passes the centroid of this rectangular 1. But I'm calculating respect to x, so I should transfer from here to here plus area 1 times 4 times the distance between two axes. From here to here it will be 2 inch squared plus, for rectangular number 2, the moment of inertia will be 6 times 2 cube over 12, but this will be respect to axis passes to centroid of this. 6 times 2 cube over 12 width times height cube over 12. I want to calculate respect to x, so I should transfer from here to here plus area for that rectangular 2. It will be 6 by 2 times the distance between these is squared. The distance, it will be 1 inch from here. 1 plus 4, it will be 5 squared. That will be our Ix. But if I want to calculate Iy and assume y is this axis, and you see it is symmetry axis and passes through the centroid of both. So this is very simple. Iy will be equal to 2 times 6 cube over 12 plus 4 times 1 cube over 12. For this rectangular, now respect to this is width 4, height 1 cube over 12, and y passes through the centroid of this. Plus, for this rectangular, 2 times 6 cube over 12, again y passes through the centroid. So there is no need for another term. So now you know, if we put material far from the bending axis, the resistance against the bending will increase because moment of inertia will increase. I can write that here. The further the material is spread from the bending axis, the stiffer a cross section tends to be stiffer means more resistance. For example, rectangular, in this direction it is not very stiffer. But if I rotate it, if I rotate and I put in this direction, now it is much stiffer. For that reason, if we take most material far from bending axis and I create I shape, this cross section will show higher resistance against the bending. This is the reason you see in the construction most steel beam as an I shape. In the wood you cannot do that because labor cost. It is difficult to make I shape wood beam. But in the steel you can do that easily. So most steel beam, you will see it is I-shaped because they try to put most material far from the bending axis, and that will increase the section efficiency. Okay. As a homework problems, find the moment of inertia for triangle shape using integration. This is B and this is H. Respect to that axis passes through the centroid. This axis, for example, this is XC. For circular shape, again, find the moment of inertia, assume the diameter is D, respect to axis passes through centroid. Of course, if you find respect to these axes using the parallel axis theorem, you can transfer to any other arbitrary axis. But try to calculate this using integration. Of course, I will calculate and you can compare your solution. Okay, thank you so much for watching this lecture. See you next session. Bye.